Okay, so I'll just demonstrate that algorithm in a toy setup right now, whatever we did, right? So this is a function that is given to us, and as you can see that this function has multiple minima, right? There's one here, there's one here, there's one here. And I'm just going to try to follow the gradient descent rule, right? Which is wherever I am currently, which is W, I'm just going to do W minus eta W, right? So that's going to be my new value. So right now I'm at a value of W, which is 1.2, okay? I have done the computation there. I have calculated the derivative, okay? So remember that derivative if of x squared, for example, right, is 2x. But now if I compute the this value at x equal to 1.2, then I get some scalar number, right? So that's what I'm going to do here. So my w is equal to 1.2. So whatever is the derivative, in that formula, I'm going to plug in w equal to 1.2 and I'm going to get some answer for what the derivative is, right? And then my eta is set to 1. So that will give me what n into derivative should be. And that value is what I'll keep changing. Okay, so let's start. And I'm not going to do this in great detail. As you can see, this is like set up as a game for you to practice and try to reach at the minima. So I'll just show you a few steps of how to do it. So now my 1.2 is what my value was. I have calculated the derivative and that eta into dw turns out to be 0.31, right? So I'll have to move in the direction opposite to the gradient. So I'll do 1.2 minus 0.31. So I'll just enter that in this box here, right? So 1.2 minus 0.31 is going to be 0.89. Okay. So this is where I end up, right? So I have moved and looks like I have moved in a good direction because I'm headed towards one of the minima, right? So 0. Now at this point, I have 0.89 is my current value. I've again computed the derivative and my eta into dw is 1.25. So I'm again just going to 0.89 minus 1.25 is what I'm going to do, and that would be around minus 0.36, right? So I'm just going to set the value as minus 0.36, and this is where I get, right? So as you can see, I have moved a bit away, right? I would have liked to end at the minima, but I have gone in the opposite direction, right? And why this is happening, what could you do to make sure that this doesn't happen, is something for all of us to figure out in the next couple of lectures, right? Now you just keep trying this, right? I've shown you what to do. You just follow this. And as I said, it's like a setup as a game. You could just keep trying this and see, right? And now you can notice, right? So far, I was moving in this direction, right? I started here, then I went to a point here, then I went to a point here, and now it looks like I have to come in the back direction. I have to come back and so on. So you just play with this and you just keep following the update rule and see that you will slowly start moving towards the one of the minimas that are there in this function, right? And you could also initialize the w from a different point, right? You could initialize it from, say, this point here, and then you will see that it will start going towards this minima. If you initialize it for a point here, it will start going towards this minima, right? So what I had done is I had initialized it at this point, right, which was on this side of the slope. So that's why it went there. If I had initialized it here at this value, then it would have gone into this minima, right? So just play around with this, try different values of w and keep following the formula and see whether you are able to reach the minima. I'm sure you will not be easily able to reach the minima, and one of the problems there is that eta is a bit large, so it's not helping you to control eta into dw. Here I wanted the eta to be small, right, so that I could have reached the minima instead of crossing it. I have crossed the minima and gone in the other direction. So all of this is something that we'll do in detail, right? And at this point, I just want you to kind of break your heads with this and try to understand the problems that show up, right? I don't want you to fully understand this, nor do I want you to get the solution, but I just want you to see what kind of problems you face and how would you change them. I already gave you a few hints, right, that you might think that, oh, this is the global minima, but I started from some point here, 1.2, and I'm not being able to reach there, right? Then what if I had initialized it a bit differently? Would I be able to reach there? So what is the effect of initialization? what is the effect of eta? As you make eta very large, what happens? If you make eta very small, what happens, right? So just try to experiment with those things and just get your hands a bit dirty with this. Okay. Yeah. So now we have the gradient descent rule that the direction u that we intend to move in should be at 180 degrees with respect to the gradient. In other words, move in the direction opposite to the gradient. So this phrase I'm sure you have heard a million times, but now you know where this phrase comes from. And this is what my update would look like. Whatever is my current value of whatever is my current value of w, I just take the gradient or the derivative, right? And then move in the direction opposite to that because of the minus here, and by a small conservative step because of eta. And this eta comes from the fact that Taylor series works well in a small neighborhood, hence we are using a small eta there, right? Now, this here, if I put it in a vector, this is nothing but theta t plus 1, okay, maybe not the best choice of colors here. If I put this in a vector, this is theta t, and if I put this quantity in a vector, then this is the gradient of the loss function with respect to theta, right, okay, at time step t, right, at the time step t, right. So now let's try to again clarify the notation. So this the entire thing I can write in vector form, that's what I've just shown. Now some more clarification. So what does this quantity delta wt mean, right? So delta wt is the partial derivative of the loss function, which is a function of two variables w and b with respect to w, and then evaluated at w is equal to wt and b is equal to bt. What does that mean? So now if I have the function is w square plus b square, then the formula would be 2w 2b, right? This is what the formulaic representation of the gradient would be. But now I can evaluate this at the current value of my w, right? So I'll just substitute the value of w, and if I do that, then I'll get two real numbers, so I'll get a real valued vector, right? As opposed to a formula, I'll get a vector, right? So this is always this, that you have the formula for the derivative, then you can evaluate the derivative at a specific point by putting it those points, that point into the formula. So that's what I mean by evaluated at w is equal to wt, right? So that's what this quantity is signifying, that it's the partial derivative evaluated at that point. And that's exactly what we were doing in the previous slide. We were getting a real number at the end, which we could add and subtract and so on, right? So that's the idea. Yeah. So now we have a more principled way of moving in the WB plane. We are no longer doing our guesswork. We know that if we do, we just saw a proof, or we arrived at the formula mathematically, that if we keep moving in the direction opposite to the gradient, we are guaranteed that the loss at every step will decrease. Not that it will just decrease, it will also decrease by the largest amount, right? Now, one thing you should have noticed on the previous slide, in my last update, actually you should go back and check whether the loss had increased or not. And if the loss had increased, what could have been the reason for that, right? And the answer there is that the learning rate or the eta was quite high. But all of these are things that we'll come back to, so don't worry about it. Okay, so this is the algorithm that we have created. We'll start at time step 0. We'll set up some max iterations. We'll initialize w and b randomly. And while we are less than the max iterations, we'll just keep doing this repeatedly, right? Whatever is the current value of w, we're just going to get a new value of w from that by following the gradient descent rule, right? And we keep doing this for the max number of iterations. And by then, we should be at a point which is very close to the minima, right? That's what the hope is. Okay. Now, everything in this algorithm is known, right? I could have actually run this algorithm. It's just that I don't know what this delta W and delta B is, right? So let's see what, I've given you the definitions of them, right? But what is that formula? How do I actually compute this, the partial derivative of W with respect to the loss function? Because I have not even told you very clearly what the loss function is in so far in the discussion, right? We are just working with a generic function L of W. So we now need to look at what the actual loss function is, right? So here's coming back to our original example where we had two parameters W and B. This was our function, okay? And our loss function was defined as this, right? That let's assume there's only one point, there's only one data point. So our loss function was summed over all the points and then taken the average. But now I've assumed that there's only one data point, so there's no summation here. And summed over what? It was the prediction minus the true and the square of that, right? So that's what this formula is. f of x is our approximation, y is the true value. So I'm taking the difference between the two and squaring it, right? And this 1 by 2 I've just kept for some convenience. It does not, I could use any multiple here, right? It does not change because I'm looking for the lowest value of the loss. Whatever is the lowest value, if I multiply all values by half, that value of w comma b, at which I get the lowest value, does not change, right? But it just makes it a bit convenient for me from a mathematical perspective. I will become clear why, how. Okay, so this is what our loss function is. Now I come to the definition of delta w, which was there on the previous slide, is the partial derivative of the loss function with respect to w, which is the partial derivative of this function with respect to w. So this is the quantity that I want to compute now, right? So this is the partial derivative. Now this is easy, right? So this I can just, I know that this is a function of w comma b, right? This is my sigmoid function which has the parameters w and b. So this is a function of w and b. So I'll just take the derivative and then push the derivative inside it. So this is the derivative of the square of a function of w. So it will just be 2 times that function into the derivative of the function, right? This chain rule of derivative that you know. So this is some function which depends on w. Then you have taken the square of that function and now you are taking the derivative. The first thing would be 2 times the function and then you push the derivative inside. So you get the derivative of the function with respect to w. Okay. Now this is of course a constant, right? Because this is the value, true value which is given to us. It does not depend on w and b. I can choose whatever w and b I want. The true value will not change. So that the derivative with respect to that will be 0. So the only thing that I am read is the partial derivative of the function with respect to the w, right? And you can see why I had chosen this half here, because this half and 2 got cancelled. It just makes my life easier. And now if I just substitute the value of f of x, so this is the value and this is the derivative that I want to compute. So let's try to compute, right? So this is the derivative of, again, of the inverse of a function of w, right? So this is 1 over something which is a function of w. So the derivative would be minus 1 over that function square and then the derivative pushed inside. So derivative of this should have been 1 plus that e raised to minus wx plus b, but 1 is a constant, so it's anyways going to, the derivative will be 0, so I have not written that, right? So now derivative of e raised to minus wx plus b, so that would be e raised to minus wx plus b into the derivative of minus wx plus b, and now again b is a constant, so that would just give me minus 1. So, minus x, derivative of wx with respect to w would be minus x. So I have these two negatives, minus 1 and minus x, so that will become a positive. Okay, so this is what I get. Now what is this? This is just my original f of x, right? So this is f of x, so I can just write f of x and you can go back and check this. This is essentially 1 minus f of x, right? So you can go back and work it out. So if you just take 1 minus 1 over this formula, right, then you will, 1 minus this formula, then you will get this, right? So I can just write it as f of x into 1 minus f of x, right? So now I'm going to substitute this value back in my original equation. So this is what I get. I had this term already from earlier and now this entire quantity is this, as I have just derived, right? So now I exactly know what delta w looks like. And now if you give me a value of w and b, I can substitute that in this formula and I can get a real numbered value, right? So I know the formula that I was looking for, okay? So if we have only 1 point, then we have the delta w is equal to this. If we had more than 1 points, then it will just be a sum of all those, right? So this is the derivative of the loss function with respect to w when there was only 1 point, right? So in that case, LW itself was just f of x minus y the whole square, right? But now if I have many points, then I'll have a summation here and I'll index this by I, I'll index this also by I, right? So I have a summation. So I have told you the derivative for one term in this summation. If there are such n terms in the summation, then the derivative will also get added up, right? So the derivative of a sum is just the sum of the derivatives, right? So that's what is happening here. So I have just taken the sum now. So if there are 2 points, I'll have just the sum here. So I have this, right? Now, similarly, you can compute the derivative of b and you can see that all of this is same The only thing extra here is this xi, and that is coming from the fact that you had wx plus b. So when you take the derivative with respect to w, this x is what you get. But when you take the derivative with respect to b, you don't get this x, right? You just get 1 here. That's why you are having this into 1 here and into x there, right? So now you have the formula for delta for the partial derivative of the loss function with respect to w and the partial derivative of the loss function with respect to b, right? So you have both of these, and now we can construct an algorithm out of this. Okay, so let's see what that algorithm is. So I started off, so this, I hope you can see it. So these were the 2 points given to me. These are the same 2 points that we have been looking at since the last lecture. So x equal to 0.5, where the value of the function was 2.5, and x equal to 0.2, where the value of the function was 0.9. Okay. Now I want to do gradient descent to find the right w's and b's. So I have set w to -2. My initialization is -2. B is also -2. I have kept eta as 1, and I have set the max epochs as 1000. Right. So this is what my initializations are. Now for I in range of max epochs, that means for 1000 iterations, I have initialized the derivatives to 0. And for xy in my data points, right? So all the data points, I'll iterate over all the data points. I'll compute the gradient with respect to w, or the derivative, partial derivative with respect to w. I'll also compute, so let's see, now I want to compute the partial derivative with respect to w. How will I do that? So I have this function here, and I know how to do this, right? So I can, this is the formula. I just computed this on the previous slide, f of x minus y into f of x into 1 minus f of x into x, right? And what is my x here? I am looking at the first point here. So my x is going to be 0.5, so I can just substitute that here. And what is my f of x? Let's see what f of x is. So this is how I'll compute f of x, right? So f of x is, I'll just substitute the value of x in this formula, and I'll just substitute the current values of w and b, right, which are 2. So I can compute this and I'll get some real number, and that is what I'll put here, right? So now I can compute that quantity. Similarly, I can compute the grad of the partial derivative with respect to b. Again, I have a function written for that, and the same idea that I want to compute this f of x, which I'll compute from this function here by substituting the current values of w, b, and the x that I am dealing with, right? Okay, so far so good. Let me just erase it. Okay, and then I'm going to sum this over all the points, right? Because I visited the first point, which was x equal to 0.5 and y is equal to 2.5. Then the loop will go to the second point. This loop will go over all points, and I'm just collecting all the, I'm just adding up all the derivatives, because as I said, this derivative of a sum is just the sum of the derivatives, right? Once I've computed the derivatives, I'm just going to apply the gradient descent formula, which is w is equal to w minus eta into the dw, and b is equal to b minus eta into db, right? So this is, I'll just keep doing this in the loop, and I'll keep moving along the error surface. So this is what my error surface is. So I have this is what my error surface looks like. And how have I plotted the error surface? I have plotted it using something like this, right? So, oops, this is a bit hard to navigate. Yeah, so this is how I've plotted for all possible values of w comma b. Actually, I've just computed the error and then I have plotted it, right? So don't worry too much about what is happening here. This is just a formula for computing the loss function, which is f of x minus y the whole square, right? So I've just computed that and I've plotted this. So now if I just keep changing the values of w and b as shown in this algorithm following the gradient descent rule, then no matter where I start from, I'll start moving in a principled way, and at every point the loss will just keep decreasing and I'll reach the minima. That is what is going to happen. And now let me try to see if I can demonstrate that, right? I'm just going to go here, okay? Okay, so this is what my loss function looks like. This is actually the same as the loss on the previous slide, just scaled a bit differently. And what I know is that I want to reach somewhere here, because in this surface it's clear that the error is minimum there. But right now I am way far. I want to reach somewhere here, but I am way far. My initialization was randomly done, right? So now what I'm going to do is I'm going to run this algorithm, and you just observe how the things change both on the loss surface. You should see that the loss at every step should keep decreasing, and the W should keep W comma B, the point on the on the W comma B plane, right? So this here is the W comma B plane. So on the W comma B plane, I should keep moving till I reach this nice optimal value here at which the loss is minimum. Okay, so let's see if I can run this. So the algorithm is running. It's initially quite slow. You can see that the yellow dots are moving, right? It's slowly moving. It has finished some 27 iterations. The loss is still a bit high. It's 0.81, as you can see here, and it's still running, but it seems to be going in the right direction. At no point am I seeing that the loss is increasing, and it keeps going. I'll just fall down. Good. The loss has decreased quite a bit, and I'm very happy that I'm moving in the right direction. Again, it has slowed down a bit. Why is it slowing down in certain regions? Why is it not going fast in other regions is something that we'll figure out. But now it has started moving, and you can see that the loss is around 0.02. I just ran it for 100 iterations. I've stopped it now. I could keep running it a bit more. This I had set it to 100, isn't it? So let me just make it 500. And I can keep running this. You can again experiment with this at your own leisure, right? So now you can see that it's moving further, and it'll keep going patiently. It'll keep going, but it'll go in the right direction, right? I'm not worried that it will eventually reach the loss function, right? Even 500 iterations does not seem to be enough in this case. But if I just run it for 1,000, 2,000 iterations, then it will reach there, right? But the key thing that you need to at least be happy about right now is that unlike your random guess algorithm, here you are not making a mistake at any point. At every time step, your loss is definitely decreasing, right? So that's what is happening here. So this is a demonstration of the gradient descent algorithm on the toy example that we had, using the code that I had on the previous slide, which was in turn based on the gradient descent update rule, right? So later on in this course, we'll look at gradient descent in much more detail, and we'll look at a lot of its variants, right? So for now, it suffices to know that we have an algorithm for learning the parameters of a sigmoid neuron. I've just shown you the algorithm. I have shown you the math behind it. I have shown you the visual interpretation of that, and I've also shown you how to code it and then run it so that you move on the loss function in a principled way, right? So I'll end this video here before just telling you quickly where do we head from here, right? So now the next thing to do, we have completed this cycle that we introduced sigmoid neuron just as we had introduced perceptron. Then we introduced the learning algorithm just as we had introduced the perceptron learning algorithm. Then we discussed the error, and we ran the algorithms in both cases, in perceptron as well as in the sigmoid neuron, and we saw that the learning algorithm actually learns well and it keeps moving in the right direction. So all of that we have seen. Then in the perceptron case, we had moved on to the representation of the power of the perceptron, and now we want to talk about the representation power of the sigmoid neuron, right? So that's what we are going to do next. So I'll end this video here, and in the next class we'll continue with the representation power of sigmoid neuron.